Okay, hi everyone. Today we're going to be talking about alcohols and phenols, but more specifically just on the class of compounds which can be generalized to be alcohols. Okay, so what do we have in store for today? So we're going to have an introduction here, and then we're going to just look at some review reactions, and then start to look at oxidation and reduction and begin to understand what that is. But before we do begin, let's have a little introduction. So if you did not know what type of alcohol goes inside of your margaritas or your White Claws or wine or whatever you prefer, that alcohol is referred to as ethanol or ethyl alcohol. So ethanol is the type of alcohol that we can drink. We can't drink any other type, okay? And if you do drink any other type of alcohol, you might die, okay? Of course, there's isopropyl alcohol, which we may be familiar with. We may be familiar with methanol or ethanol, but those are not to be confused with the purpose of ethanol. So by the end of this chapter, we will have described what really causes a hangover and what we can do to prevent it, or what we can try and do to prevent that. And then for those who have seen the movie The Hangover, I saw this one when I was a kid. I remember that my mother had let me watch this with her in the movies, and I just remember seeing so many things that I did not understand, but it was a great movie series back when I was maybe 11 or 12. Okay, so let's begin. Um, Alcohols, they are everywhere in nature. So here are just a few examples. We have this drug molecule. It's an antibiotic, and you see that alcohols are appearing here, right? If you're planning on going into any kind of medicine um, or dentistry, veterinary, or even just chemistry itself, you're going to need to know how to work with alcohols. They will pop up everywhere. We have cholesterol, which is a precursor to vitamin D upon a ring opening reaction, but we have cholesterol here, hence the suffix or the suffix at the end of the name. The cholesterol indicates that you have an alcohol attached to this four-membered ring, and we all know what cholesterol does. And then we have cholecalciferol, which will regulate our calcium levels and helps to maintain strong bones. There's also other ones that pop up, like estradiol, and of course that is secreted by the ovaries. Okay, so let's look at a few examples of phenols now. We have here, I don't know how you exactly pronounce this. I'm pretty sure it's capsaicin or capsaicin, but in general, this compound is responsible for that spicy or hot flavor that we, whenever we bite into the chili peppers. So this is really what is interacting with your body. Interestingly enough, something like this creates this kind of spicy or hot effect. And then there's THC over here. Some of you have firsthand experience with this. I know Duff does. Um, and so you can see that phenols, or in general, an aryl alcohol, is appearing in this compound as well. So phenols and alcohols, they're very, very important. If we're going to have spent a whole year in 2 courses in organic chemistry, we better know how to do some reactions with alcohols, right? We need to know how to manipulate them to get to some kind of desired product. Okay, so let's speak about nomenclature just for a moment before we go and do some examples. We learned from chapter 4 out of the textbook that we can name hydrocarbon chains with a few substituents on them. We got very good at that. We're now going to learn how to name alcohols with them. So as you can see here, we have pentane, just a 5 carbon ring. And if we put an alcohol at the first position, that would be called pentanol. Or we could call it 1-pentanol. So it would look like this, but you replace the 3 with a 1. So this is 1-pentanol, or just pentanol. If you just say pentanol, it's assumed that the alcohol is at the first position, but you don't have to explicitly write that number. If the alcohol, however, was at the third position, then you would write 3-pentanol. Or you can say pentan-3-all. The same applies up here. You could say pentan dash 1 dash all for this compound right here. So there's many, many ways to name this. In fact, I believe there's 3 ways to name this kind of pentanol, and there's 3 ways to name, or then there's only 2 ways to name this one. Okay, so then let's look at this compound right here. So our parent chain, interestingly enough, is not the benzene, right? Usually we take the benzene ring to be our parent chain, but in this case, we have an alkyl chain coming off of the benzene, and it has a couple substituents of its own. In fact, there's an alcohol. So we're going to name this 3-membered carbon chain right here as the parent chain, and alcohols will always get first priority, okay? At least just in a compound containing alcohols, halides, and carbon, and double bonds, the alcohol will get that first priority. So we simply number our ring, and then we say at the first position we have an alcohol and it's 3 members, so that's a 1-propanol. That's what goes right here, that's our parent name. At the second position we have a rectus and it's 2-chloro, hence the R in parentheses dash 2 dash chloro, and everything is alphabetized here. And at the third carbon we have that phenol group. Okay, so you can put this all together to obtain such a name. If you have a ring with only alcohol in it, you can simply just call it the cyclo membered ring with the OL at the end. So cyclopentanol is used as an example here. If you had a 3-membered ring, that would be cyclopropanol. For a 4-membered ring, that would be a square. That is cyclobutanol, and so forth. Okay, so these are just a few examples. This is simply just review up here if you're still confused. You should not be at this point, but in case you have forgotten or need a refresher, this is how we can choose between whether an alcohol is going to be primary, secondary, or tertiary, just by judgment of how many carbon groups are coming off, or how many carbons are located at the beta position relative to the alpha position of that alcohol substituent. Now let's go over here for a moment and we'll talk about phenol. This is an aryl alcohol, but in general we call this a phenol, okay? That's not to be confused with this right here, which is phenol. It is called phenol when it is a substituent, and phenol has nothing to do with that, okay? So phenol versus phenol. And we already learned how to name this back in chapter 17 and 18. So we can see that this one here, we're choosing phenol to be our parent, and para to that alcohol is the 4th position, and it has a chlorine. And then at the 2nd position, that's an ortho relationship to the alcohol. So that's the 2nd position over. We have a nitro group. So you alphabetize that all together and you can name your such compound. So we don't want to call this benzene alcohol. We have a more general name. So these are acceptable IUPAC names, although they aren't formally an IUPAC name like, 2 dash, 3 dash, whatever. We just call it phenol. Okay, so whenever you see a benzene with an alcohol attached to it, that is a phenol functionality. We have isopropyl alcohol, okay, right here. So this is isopropyl alcohol, or the IUPAC name would be 2-propanol. We have tert-butyl alcohol. You can also call this tert-butanol, right? You can call this isopropanol. And here we have 2-methyl-2-propanol. So at the 2nd carbon we have a methyl, and at the 2nd carbon we have our alcohol, hence the 2-methyl. And then at the 2nd position we also have this alcohol attached to propane, hence the 2-propanol. And then this right here, this is not phenol, so try not to be confused with this. This is phenol when the alcohol is directly attached to the benzene ring. But if the alcohol is attached to a benzylic position, it's referred to as a benzyl alcohol. Okay. So let's diverge for a moment and speak a little bit on acidity and stability. So from very, very early on, we understood that as the pKa of a compound, okay, falls, so as the pKa grows lesser and lesser in value, then we have increasing acidity with that. So they're directly proportional. If our acidity is increasing, we know that the pK is decreasing and vice versa. Okay. So when that pK is a really low number, let's just say it's -10 here, okay? We're looking at our halo acids. So when it's approximately -10 plus or minus a few units, and that's super low, okay? We have our halo acids. That's hydrobromic acid, hydrofluoric acid, hydroiodic acid, and so forth. So those are really, really acidic compounds. If we look at pKs, which are, we can just say about 16 here, okay, but in general between 15 and 18, we're looking at the alcohol compounds. So they're not really acidic, but they can be acids in certain situations, okay? So a good way to remember the pK of alcohols is that you usually start to try alcohol between the ages of 15 and 18 once you get into high school. So that's a good way to memorize the acidity of alcohols. For our amines, not to be confused with amides, but our amines, okay, the pK falls somewhere around 36, so between these two values, but somewhere around 36 plus or minus a few units. So we can see that this is more so going to act as a base, right? It's not really acidic per se, but it's probably going to function as a base here. And then if we have carbon compounds, so carbons just with hydrogens, just a normal hydrocarbon chain, we're looking at a pK which is approximately 50 and up. So this is obviously not going to function as an acid, right? An acid gives up the hydrogen. An acid gives away that proton. So it makes no sense to talk about carbon chains as really being an acid at this point in our understanding of chemistry, not at least until we get there. So carbon's really never going to function as an acid, but alcohols and halo acids, they're going to be an acid. And of course, alcohols in certain situations can act as bases. It's all relative to the two molecules that you're using. So say, for example, that we had a halo acid and an alcohol, and I put them together in a pot, okay? Well, what's going to act as the acid here? Is the thing with a pK of about 16 going to be the acid? Or the thing with a pK that's less than 0? Well, of course it's going to be this one right here. The halo acid is going to lose its proton, right? The lone pair on this oxygen is going to snatch off that hydrogen, and then the two electrons in this sigma bond are going to jump onto the halide, okay? And it will form an ion, okay? So you can see here that just from the argument of pKs, which is a qualitative argument, we can clearly see that um, the halo acid is going to be the acid in this case, okay? And will therefore then become the conjugate base once it is deprotonated. If we look at the stability here, we can also see a trend. So we see that that negative charge, or in general the molecule, is more stable, okay, when it's on a more extreme level. So when it's deprotonated, when all these things lose their hydrogen, we can see that there is an increasing stability when it wants to react. So I guess it has a greater opportunity cost. It has more to give up here, but it can become more stable in the end, right? This guy is the most reactive of them all as an acid, but once he gives away that hydrogen, man, does he become stable. So this is just an important thing to recognize as we move forward. Let's begin to talk about the conjugate base of an alcohol, and then what these alkoxy groups are. So the conjugate base is simply when you remove that thing's hydrogen. So if we have this alcohol here, and we decide to remove this proton, so something, let's say that this alcohol functions as an acid, so it is giving away its proton, then something will snatch that hydrogen, and the lone pair from the sigma bond from the oxygen to the hydrogen, those two electrons jump onto this oxygen and they form this, right? This is what is referred to as an alkoxide ion, okay? This is referred to as an alkoxide ion. So how can we really make sense of this, right? Look at these groups right here, okay? This is a hydroxy group, or in other words, it's an alcohol. If we have a methyl group attached to an oxygen, attached to just some other carbon chain, we can call that really a methoxy group. We can call an ethyl chain attached to an oxygen an ethoxy group, oxygen attached to 3 carbons, propoxy, and so forth. But what we're really interested in is this box in green here. Let's say hypothetically that all of these R's were hydrogens. So now it would be methanol, ethanol, propanol, and then water, which is really like a derivative of alcohol, right? So these are alkoxy groups, okay? So we've seen that a deprotonated alcohol compound forms an alkoxide ion. So let's apply this alkoxide, and these are alkoxy groups. Well, again, if all of these R's were hydrogens, then what happens when water is deprotonated? That becomes hydroxide. What happens when the methanol, so a methanol, this is an H, if that hydrogen is taken away, it now forms methoxide. This one would be ethoxide. This one would be propoxide. You see, the ending of the alkoxide implies what charge that thing will have. So if it's methoxide, you know it has a negative charge, this oxygen, as we see with the alkoxide ion over here. Okay? But in general, these groups are called alkoxy groups. So we have alkoxy groups, we have the alkoxide ion. That helps us to just understand the terminology moving forward. Okay? This is just a generalism. We won't go too much into this, but this just shows how do we deprotonate the alcohol. Let's say that I want the alcohol to function as an acid. So it gives away its proton. As you can see, it's losing its proton. That makes ethanol the acid here. You can use something like sodium hydride to simply rip off the hydrogen. You can use sodium amide, which is NaNH2, okay? Or you can use a stronger base like a methyl lithium, but that of course is super strong, so maybe we want to stay away from that. You can also just put the alcohol in a spectator ion like sodium or potassium or lithium, and it will sort of just form this ionic bond here. Okay, so this ionic relationship. So let's go ahead and look at a few things here. You can go ahead and draw these, but I'm going to go ahead and draw them on the next slide. I have prepared this for us. So let's say that we want to look at some of those examples. So I'll draw the first one here. Okay, so we have, and you can name this. This would be a 6-membered ring with an alcohol. This is called cyclohexanol. And we're going to go ahead and put it with some sodium, pair it up, and we're going to form the alkoxide ion. So it would simply be this, and then the sodium, it's sort of forming this salt. So we just simply put it with a spectator ion, and it will just complex like this. Okay, let's look at another example. Let's try tert-butanol, and we can go ahead and pair it up with lithium. That's also another spectator ion. Well, what's going to happen is the same thing. We're going to just simply form that alkoxide ion, right? And you may recognize this, right? This is tert-butoxide. So now you see how we're starting to put the names together. Whenever it ends with oxide, we have a negative charge in that oxygen. So this one here is going to be called tert-butoxide, okay? We've seen that before with our E2 reactions. But let's look at ripping off that hydrogen. Let's not put them with spectator ions. So when we put the alcohol with the spectator ion, it just forms the alkoxide ion. But we can also form the alkoxide ion from simply just putting it with a very strong base. So let's remove this hydrogen, okay? Let's remove this hydrogen using a very strong base. So we're going to use sodium hydride here. Sodium hydride. So the sodium, of course, is just a spectator. So it doesn't really do anything in this reaction. So we can go ahead and just sort of mark it out, right? The sodium doesn't do anything to help us. We're just focused on the hydride, okay? Now you'll notice something. Alkoxide has a negative charge. This is hydride, so it's also going to have a negative charge. So this, right, this hydride here really looks like this. Has a negative charge, and it has one lone pair on it. This is a very, very strong base. And so what's going to happen is it's going to yank off that proton, okay? And in the process, that lone pair is going to get pushed onto the neighboring oxygen atom. This will form an alkoxide ion. Okay. Of course, if oxygen is bonded to one thing, it will have 3 lone pairs. So this one also has 3 lone pairs, and this one also has 3 lone pairs, trivially. We'll look at the last case where we have this cyclobutanol molecule. So we have cyclobutanol here. And it says that we can use sodium hydride, but I'm going to show you another base that is typically used in organic chemistry, and that would be sodium amide. So it's NaNH2. Again, ignore the spectator ion. It doesn't matter if this was lithium amide or potassium amide or sodium amide. The spectator just simply spectates, okay? Doesn't do anything. But now we want amide. So we're going to want that negative charge on that nitrogen. So I'm going to draw it up here as NH2 with a negative charge. So this one's going to have 2 lone pairs. It's very, very electron rich, right? That's what that negative charge really tells us. It's electron rich. And what do really strong bases like this do? They're going to tear off the hydrogen. So he simply reaches for the hydrogen, snatches it off, and pushes those 2 electrons from the sigma bond onto the neighboring oxygen. So we already had 2 lone pairs here, and now we're going to gain our third one to form that alkoxide ion. Okay, so that's just some good practice for you, but you'll see this pop up in lots of places. The reason why alkoxides are so important in organic chemistry and in general alcohols is because if we can prepare these alkoxide ions, then we can use these now regions of very high electron density to attack something else. We can form an ether off of this, for example, and we'll see that in reactions to come. So that was just one way that we could sort of practice what was going on. Okay, good. So let's move on. Let's talk about phenol and cyclohexanol and just some sort of patterns that we notice. So if you look at cyclohexanol here, you will notice that cyclohexanol has no double bonds, there's no ring here, and its pK is 18. So this alcohol's pKa is 18. So it's a little higher than 16 we can see, maybe because of its steric hindrance. But you look at phenol here, and it has a pK which is 8 times or 8 values away lesser than this one. So phenol, right, a lower pKa indicates that it is more acidic, and a higher pK indicates that it's not as acidic. So phenol is 8 orders of magnitude more acidic. So phenol is 10 to the power of 8 times more acidic. I think that's 10 million times more acidic than cyclohexanol. That means if it was a competition between which one of these two would get deprotonated first, the phenol is definitely getting deprotonated first. And why is that? Well, let's go ahead and look over here to this just three things that I put down. If something can do or has resonance, induction, or can undergo solvating effects, it will generally be more acidic. So let's discuss that in the next slide. Let's reason as to why we know that phenol is more acidic than cyclohexanol. Resonance. So this is the big one. We will notice that if the cyclohexanol is deprotonated, Are there any resonance structures that you can draw? Well, you say no. There's no pi electrons to push around, Sammy. So there's really no like good resonance structures that we can draw on this molecule. You say we can't delocalize the pi electrons around the molecule, right? We can't let them sort of move freely in their close proximity. So it can't even do resonance. And resonance stabilizes that negative charge. But when you look at the phenol in its ion form, so this is now an alkoxide ion, but it's a phenoxide ion, okay? A phenoxide ion. We see that there is 5 resonance structures of this molecule. 5 resonance structures. So that negative charge is going to activate this ring. It's going to push the electron density into this ring, okay? And we now understand from chapters 17 and 18 what an activated and deactivated ring is, okay? I may have misspoke. I 10 to the power of 8. It must be 100 million times or 10 million times more acidic, but you get the point. You're never going to find cyclohexanol deprotonated before you find the phenol deprotonated. Okay, so resonance really does matter when assessing the conjugate base's stability. If we look at induction, it's just something as simple as saying when there are more electron withdrawing groups in the neighborhood of our protons that could be grabbed, well, notice that when you put really electronegative atoms near that group which is going to give away its hydrogen, it becomes more acidic, simply from the principle that the electron density from this hydrogen, right, it's being torn away in this direction. So it's being torn to the left here, and in that process, it deshields the hydrogen. When it deshields that hydrogen, it can be attacked, right? If the shields are down, it's going to be attacked. And so you can see here that this one is about 1,000 times more acidic than just ethanol. And so that can be important, right? If we want to make sure that something is going to get protonated. But maybe we didn't want too strong of a base. So that's why things like this might be useful. So this is simply just an electron withdrawing effect, electron density withdrawing effect. So induction by definition is the flow of electron density through the sigma bonds. So there's a lot of induction going on here, whereas in this case there's not really a lot of induction. Okay, so let's continue again. And we'll just look at solvation effects. So this is mostly the boring part of this chapter, but let's just get through it real quick. All that it's saying is that, let's say that we have 2 alcohols. Now we've seen alcohols can range from about 15 to 18 in their pKa's. Of course, ethanol is 2 orders of magnitude more acidic. So it's 10 to the power of 2 times more acidic, that's 10 squared. So ethanol is 100 times more acidic than terbutanol, and that can really matter in the lab, right? But why is that? The first thing you're going to say is steric hindrance. Okay, plausible. Let's go ahead and look at what's going on over here, okay? Well, read this sentence with me. This difference in acidity is best explained by a steric effect. The ethoxide ion, this alkoxide ion right here, isn't sterically hindered and is therefore easily solvated. So when something is solvated, that means that the solvent can surround that negative charge, not necessarily binding to that, right, getting bound to that oxygen atom, but by a non-covalent effect is sort of stabilizing that negative charge, okay? So when we have something that is sterically hindered, like tert-butoxide, okay, we can see that our chicken foot here is sort of blocking out the solvent. So not as much of the solvent can surround this alkoxide ion, okay? So this is simply just the explanation and difference of the acidity here is explained by the alkoxide ion's ability to be solvated. Okay, so let's go ahead and look at a few questions from Duff's exam and see if we can answer them now. So The first question says, rank the following in order of decreasing basicity. So the most to the least basic. So we're going to go ahead and write this down on a piece of paper. You can just write out lithium amide. You can write down, what is this? This is a methanol that was deprotonated, and now it's complexing with a lithium ion. So this is methoxide. And this one is water that was deprotonated, so it's a lithium hydroxide. So this is a hydroxide alkoxide ion. This one's the methoxide ion. And this one's a lithium amide, so there is a negative charge in the nitrogen. This one is not an alkoxide. Only when the alcohol derivatives have been deprotonated are they called alkoxides. So I'll go ahead and write this down on a paper so that we can begin to investigate it. And so let's go ahead and do that now. We have lithium amide. We have methoxide, lithium methoxide, and then we have lithium hydroxide. Now you can also write out these things to be, well, the lithium goes away, so we just have that amide part that really matters, and that has a negative charge. Lithium amide. Then we have the lithium methoxide. So this would look like so. This one is an alkoxide ion. And then we have the lithium hydroxide right here. So this one would look like this. So the question is asking, rank the following in order of decreasing basicity. Okay, so you're thinking to yourself, decreasing basicity, a decreasing basicity. That means that the one that is the most basic, okay, is the most likely to grab a hydrogen. So we need to go ahead and maybe either look at the pKa values or assess them qualitatively. You can choose either one, okay, but if we remember from the PowerPoint the pKa's of these values, okay, we will notice that the NH2, okay, it had a pK of somewhere about 35 to 40. And in general, I just say 36. If we look at the methanol, it was about 15 to 18, right? And then this was another one, water, or the alcohol derivative, and this was also something like 15 to 18. Okay? It's about 15 to 18. So which one is the most basic here? Which one wants the hydrogen the most? This guy. This guy wants the hydrogen the most. You can see that he has a high pKa number, which corresponds to being less acidic. So he hates being like this. He would do anything to get a hydrogen again, right? He would do anything to get a hydrogen again because he has such a high pKa. So he is the most basic. So let's write that down. Most basic. Which means that he is trivially the least acidic. So if this guy was NH3 and he had the hydrogen, he would be the least acidic. Okay, now let's look at these two examples. Well, their pK ranges are following in the same places, Sammy. What do I do? Okay, well, do we have resonance going on here between either of these two molecules? And you say, no, we don't have resonance going on between these two molecules. Okay, well, what about induction? Do we have induction effects? I don't see any any halogens out here that are really trying to tear away the electron density. I don't see that. Okay, well, let's think about solvating effects. Which one is more sterically hindered? The methoxide or the hydroxide? And your answer would be the methoxide. It's a little bit more sterically hindered. So this one could be solvated less. In fact, this one is more basic. So this one is more basic than the hydroxide, okay? In fact, another pK value that you might want to add to your list is that water, or hydroxide in general, has a pK of 15.7. So it's actually a little bit less, and that's why this range goes from really 15 to 18. This one's probably somewhere at just about 16. This one's probably going to be at about 15.7. So if you want to rank these in terms of most basic to the least basic, you're saying what is the most likely to grab a hydrogen and what is the least likely to grab a hydrogen. This guy is the most basic. He is the next most basic, and then this guy is the least. So this guy is the least basic, which means that he's the most acidic. So we've now answered our question. So keep this in mind. And we know that most to least is going to be NH2, the methoxide, and then the hydroxide. So we can now return back to our PowerPoint. Okay, so I will pull that up here. Here it is. And we will look at this right here. And so an order of decreasing basicity, most to least basic, you would say is 1 is greater in basicity than 2, which is greater than 3. So your answer here is going to be A. Okay, without even writing anything down, let's look at the next question. This is from a different exam. He has the same question, order of decreasing basicity. And you see that we have the methoxide, which is about 16. We have the amide, which is about, the lithium amide, which is about 36. So we have 36, we have about 16, and then this is methyl lithium. This one is about 50. So carbons hate having that negative charge in them, okay? So this guy is 50, this guy right here is 16, and this one is 36. The lower the pK, the more acidic. So the higher the pK, the more basic. So the most basic one here is going to be methyl lithium. This is the most basic. Then it comes to this guy, the lithium amide. This one is going to be the next most basic. And then in last place comes this methoxide. So your answer from most to least basic is going to be 1 is greater than 3, which is greater than 2. So your answer here is going to be B. Okay, let's move on. So I'm going to go ahead and stop the video here, but right after this is going to be probably the most important part. We're going to be talking about oxidation and reduction, and then just giving you a little bit of a refresher on Organic 1. In fact, we're going to be doing some naming practice, so it'd be good for you to watch that video as well. Okay,